Hello everybody, it's Homer White back again with the second part in Chapter 8 of our course. This is on probability and sampling. In this second part of Chapter 8, we're going to step aside and address a special topic. How do you define one of the basic 5 parameters when you're performing an experiment? This can differ somewhat from when you're performing a regular observational study. There are 2 cases we're going to consider. One is where the subjects in your experiment can be thought of as being like a random sample from some larger population, and therefore might be representative of that population, so that the results of your experiment could carry over to and be applied to that larger population. The other case is where the subjects are not representative of any larger population at all. This can often happen to you when you do an experiment, particularly with human subjects, because it's sometimes difficult to obtain the consent of people to be in an experiment. And those people who consent to participate in an experiment may differ from the population in general in ways that are relevant to the outcome of the experiment. When you're working, always remember to make sure the necessary packages are loaded. So let's look at the first case, where subjects are a random sample from some larger population. When we discuss this case, and when we discuss the other as well, we're going to limit ourselves a little bit in terms of the experiments we think about. We'll just think about experiments where there are 2 treatment groups. Those 2 treatment groups will always correspond to the 2 values of the explanatory variable. So we'll just be looking at experiments where the research question had an explanatory variable with 2 values. If that's so, then we're only going to be dealing with 2 of the basic 5 parameters. We might be looking at the difference of 2 means, mu1 minus mu2, or we might be looking at the difference of 2 proportions, p1 minus p2. There are certainly a great many more interesting experiments out there, but we'll just limit ourselves to these 2 and start off small. We're going to introduce a data frame that's a slight variant on the familiar Math 111 survey. Its name is Math 111 Survey Fall 2012. So you'll want to learn about it in the usual ways. Use the data command to load it into your global environment. Use the view command in RStudio to take a look at it. And use the help command to learn more about the data frame and what all the variables in it mean. Now, for purposes of this course, we'll just imagine that the 89 subjects in this survey are a random sample from the Georgetown College population at large. So one question on the survey that everyone was asked was to estimate the population of Canada. But what the subjects did not know at the time when they were filling out the survey was that not all of them were looking at the same survey form. Some folks were looking at a survey form where they were asked, the population of Australia is about 23 million. What do you think is the population of Canada? And the subject was to give their answer in millions. But some other subjects were looking at a form that read, the population of the United States is about 312 million. What do you think is the population of Canada? So not everyone was looking at the same form. Since the researchers were able to randomly assign forms to students, with respect to the question about Canada, this study was an experiment. What's going on here concerns the notion of an anchor. An anchor is a piece of information that might have some influence on the way you process or think about other information. So for one group, the population of Australia, which is a fairly small number, was the anchoring information. And for the other group, the population of the United States, a rather large number, was the anchor. And the research question that we had in mind when we gave the survey was, for Georgetown College students at large in the population, are estimates of Canada's population going to be affected by the anchoring information that you have in hand when you're asked that question about Canada? So we'll do our variable analysis. Clearly, the explanatory variable in this research question is the variable anchor that appears in the Math 111 Survey Fall 2012 data frame. It's a factor variable with 2 values, Australia and United States. The response variable is the variable Canada, giving the subject's estimate of the population of Canada in millions, and that's a numerical variable. So here's how we might approach defining the parameters of interest. Let's let mu1 be the mean estimate of the population of Canada given by all Georgetown College students if somehow you could have gotten them all to take this survey and given them the form with the Australia anchor. Let's also let mu2 be the mean estimate of the population of Canada given by all Georgetown College students if somehow you could have gotten them all to take the survey but given them the United States population as the anchor. Naturally, we'll be interested in mu1 minus mu2. So, in this experiment, we imagine that there's only one population. It's all Georgetown College students. But we imagine that that population could be treated in two different ways. Everybody gets the Australia anchor, or everybody gets the United States anchor. The two parameters that we've defined both describe the single population, but it's been treated hypothetically in two different ways. And that's how we got two different parameters. This is a pattern that you'll often find when you think about parameters for a randomized experiment. We need to think how chance is playing into this. Certainly the subjects are a random sample from some larger population. We've stipulated that. But there was also chance in how the subjects were divided up into their two treatment groups. When you think about this, you realize that we don't actually have the situation of two independent samples from two different populations. We really have one sample from one population and then a division. And once you know that someone has gotten into, let us say, the Australia anchor group, you know that person won't be in the United States treatment group. And so there's a certain lack of independence in the two samples. But statistical theory shows that if the treatment groups are relatively small compared to the population from which they're drawn, and if the subjects really were randomized into their groups, then the standard probability still works. In particular, the formula for the expected value of the difference of sample means, x1 bar minus x2 bar, is still valid. And the formula for the standard deviation of x1 bar minus x2 bar is still approximately valid. So we're still okay to do the same basic probability. We're just thinking about the parameters in a little bit different way. Now let's turn to the case where the subjects in an experiment can't be considered as representative of some larger population at all. For this, we might go to the knife or gun block data frame that you learned about a little earlier in the course. Remember, this was a hypothetical experiment where you imagine there's 20 subjects who've agreed to take part. And the research question was, what's going to make you yell louder, getting killed with a knife or getting killed with a gun? And of course, all the subjects, hypothetically, were killed one way or another, with a knife or with a gun. And the volume of their dying screams was recorded as the response variable. So obviously, in this case, the 20 subjects are not a random sample from any larger population. After all, who volunteers to be killed? Maybe these are the only 20 people in the world who would agree to be part of this experiment, and their mental state is certainly not like that of the rest of the population, so we really can't imagine that the way they react to being killed with a knife or killed with a gun is necessarily similar to the way people in the general population would react to being killed in these ways. Okay, think again about the treatment groups. Remember, we have one group of 10 subjects that was slain with a knife, and the other group of 10 subjects was slain by a gun. People were randomized into those groups. The research question was, what makes a person yell louder, being killed by a knife or being killed by a gun? And so we soberly go through our variable analysis. The explanatory variable in the data frame is the variable group. It's a factor variable with two values, knife and gun, depending on which treatment group the subject got randomized into. And the response variable is the variable volume in the data frame, and this is supposed to be the loudness of the expiring subject's cries. Now that's a numerical variable. So let's think about how the parameters are going to go. Let's let mu1 be the mean volume of dying screams for all 20 subjects if all of them could have been killed with a knife. And let's let mu2 be the mean volume of dying screams for all 20 subjects if all of them could have been killed with a gun. and we're interested in mu1 minus mu2. So just as in the first case, we really have one population and we imagine it treated two ways. But because the 20 subjects are not representative of any larger population, we think of that one population as just those 20 subjects, the 20 people who volunteered to be part of this crazy experiment. And we imagine what would be the mean measurement if all of them were killed by a knife. And we imagine what would be the mean measurement if all of them were killed by a gun. And then we ask about the difference between the two. So the analysis is quite similar to the first case where subjects could be considered representative of a larger population, but we have to be careful to remember that the results of this experiment won't apply beyond the 20 subjects themselves. We might find, when we analyze the data, that the method of slaying makes a difference in the volume of the dying screams for those 20 subjects, that difference was too big to be explained just as a matter of chance variation in who got assigned to which group, that there was something real about the treatments that made that difference. And yet we might not be able to conclude that we would see a similar thing out in the general population. Let's look a little more deeply into considerations of chance here. In a way, things are even worse than in the previous case. Our two samples, the two treatment groups, are not independent at all. Once you know which 10 people are in one treatment group, you completely know which 10 people are in the other treatment group. However, the subjects were randomized into these groups. Now, statistical theory says that as long as the subjects are randomized into the two treatment groups, then the formula for the expected value of the difference of sample means is still valid. The formula for the standard deviation of the difference of sample means is also still approximately valid, but it's usually a bit larger than the real standard deviation. The larger the treatment groups are, the less that difference is going to be. So even when we're doing a randomized experiment on a relatively small number of subjects who aren't representative of some larger population, we'll still let ourselves use the formulas for expected value and standard deviation that we've already learned. But there is one final note, and this applies to any experiment at all. If in addition to the randomization you employ a blocking scheme so as to make the treatment groups look quite similar with respect to some variable that you've chosen, then the formula for standard deviation that we have learned so far is actually too large. The real standard deviation of x1 bar minus x2 bar will be smaller than the formula we've learned, sometimes a good bit smaller, depending on how effective the blocking is. So although it's okay at this point in your studies to use the standard formula for the standard deviation of x1 bar minus x2 bar as a guide to your thinking, just keep in mind that in later courses, when you encounter fancier statistical routines that deal specifically with blocking in experiments, the mathematical formulas that underlie the results you see are different and are more accurate. Thank you for listening.